Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts like construction, classification and working principle of DC machine, induction machine and synchronous machine. Slide 1. Introduction to electrical machines. An electrical machine is a device that either converts mechanical energy into electrical energy or electrical energy into mechanical energy. This is the foundational definition every student should clearly understand. There are two main categories: DC machines, which operate with direct current, and AC machines, which include induction and synchronous types and operate with alternating current. A generator converts mechanical energy, like rotation from a turbine or engine, into electrical energy. Think of it as something that produces electricity. A motor works the opposite way. It takes electricity and uses it to produce movement or mechanical energy. Examples make it easier to relate. A DC motor is found in toys or cordless drills. An induction motor powers most ceiling fans. A synchronous generator is used in power plants to supply electricity to the grid. These machines are significant in nearly all modern technology, from small gadgets to heavy industries. Their classification depends mainly on the type of current they use and their internal construction. Slide 2. Construction of DC machine. A DC machine has multiple key parts that work together to perform its function. Here's what each part does. 1. Yoke, the external frame that protects the machine and holds everything together. 2. Armature core, the rotating part of the machine. It's made of laminated steel sheets to reduce a type of energy loss called eddy current loss. 3. Armature winding, copper wires wound in slots of the armature core, where current flows. 4. Commutator, a special mechanical switch that converts the AC induced in the rotating armature into usable DC output. 5. Brushes, usually made of carbon. They maintain continuous electrical contact between the rotating commutator and the external circuit. 6. Field poles and windings. These create the magnetic field using DC supply. The poles are fixed, and the windings are placed on them. 7. Bearings. These support the shaft and reduce friction during rotation. 8. Shaft. Transfers mechanical energy to or from the armature. Example. A DC drill uses this type of machine internally to function. This construction ensures both generation and motor actions can occur depending on how the machine is connected. Slide 3. Working principle and classification of DC machine. The working principle of DC machines is based on two main laws. 1. Faraday's law of electromagnetic induction. This law states that a voltage, called EMF, is induced in a conductor when it moves through a magnetic field. 2. Lorentz force law. It explains the force experienced by a current-carrying conductor in a magnetic field, which causes motion in motors. In DC generators, mechanical rotation leads to the generation of electrical energy due to induced EMF. In DC motors, electrical input causes a magnetic force on conductors, which makes the armature rotate. Classification depends on how the magnetic field, excitation, is provided. Separately excited, field winding gets power from a separate DC source. Self-excited, shunt wound, field winding in parallel with the armature. Series wound, field winding in series with the armature. Compound wound, a combination of both, offers better performance. Compound machines offer the advantages of both series and shunt configurations, such as better starting torque and stable speed. Applications. DC machines are useful where variable speed and torque are needed, like in cranes or battery vehicles. Excitation is a new term here. It refers to how the magnetic field inside the machine is generated. Slide 4. Construction of induction machine. An induction machine, also called an asynchronous machine, has a simpler and more robust construction compared to a DC machine. 1. Stator, the stationary part that has three-phase windings. This is where the AC supply is connected. 2. Rotor, the part that rotates. There are two types. Squirrel cage, most common, simple and rugged. Wound rotor, has windings connected to external resistors. 3. Air gap, a small space between the stator and rotor, which allows magnetic field to pass. 4. Frame, the mechanical body of the machine that holds everything. 5. Shaft, transfers mechanical output from the machine. 6. Cooling fan, ensures the machine doesn't overheat during operation. 7. Bearings, support the shaft and allow smooth rotation. 8. End shields, cover and support the rotor ends. Example, induction motors are used in water pumps, refrigerators, and air conditioners. This simple yet effective construction makes induction motors ideal for domestic and industrial use. Slide 5. Working principle and classification of induction machine. The working principle of an induction motor is electromagnetic induction. Here, the stator is energized with AC supply, which produces a rotating magnetic field. This changing magnetic field induces a current in the rotor, without any physical electrical connection between the stator and rotor. Due to this induced current, the rotor starts rotating. However, the rotor never catches up to the stator's magnetic field speed. This difference is called slip. There are two main types. Single-phase induction motor, used in homes, for fans and small appliances. Three-phase induction motor, used in factories, pumps, conveyors. Squirrel cage rotor is widely used because of its rugged design and low cost. Slip is important. It's the percentage difference between synchronous speed and rotor speed. More slip means less efficiency. Significance: these machines are reliable, low cost, and need little maintenance. Applications: found in washing machines, compressors, elevators, etc. Slide 6. Construction and working of synchronous machine. A synchronous machine is a special type of AC machine in which the rotor speed is synchronized with the frequency of the AC supply. Construction involves 1. Stator. Like in induction machines, it has three-phase windings. 2. Rotor. Either cylindrical or has projecting poles, salient poles, powered by DC supply. 3. Exciter. A small generator that supplies DC to the rotor windings. 4. Slip rings. These transfer DC from the external source to the rotating rotor. 5. Air gap. Space between stator and rotor to allow magnetic flux to flow. 6. Working principle. Once the rotor reaches a certain speed, it locks into step with the rotating magnetic field. This is called synchronism. 7. Rotor speed equals synchronous speed, no slip is present. 8. Used as both a generator, more common, and as a motor. 9. Example, used in hydro, thermal, and nuclear power plants to generate electricity. This machine provides constant speed, making it ideal for power generation. Slide 7. Differences: DC machine vs induction machine vs synchronous machine. This slide helps compare the three types of machines. 1. Current type. DC machines use direct current. Induction and synchronous machines use AC. 2. Commutator. Only DC machines use a commutator to convert AC to DC internally. 3. Starting. Induction motors are self-starting. Synchronous motors need external support to start. 4. Speed. Synchronous machines run at constant speed. Induction motors run at a slightly lower speed due to slip. 5. Control. DC machines offer excellent speed control, useful in applications like traction or elevators. 6. Applications. Synchronous generators are standard in power stations. DC generators are used in labs or specific control systems. 7. Maintenance. DC machines require more maintenance due to commutator and brushes. 8. Efficiency. AC machines, especially induction, are generally more efficient. 9. Cost. DC machines are costlier due to more complex construction. This slide gives a clear comparative understanding useful in real-life selection of machines.